Good afternoon, everyone. My name is Qingxin Ye from Renmin University of China. Today, I will present our work on key-value data collection with local differential privacy. It is a joint work of Renmin University of China and Hong Kong Polytechnic University. In this talk, I will first introduce some background knowledge of local differential privacy. Based on this, I will present our practical motivation and problem statement. Then I will give our solutions, including a baseline approach to iterative models and an optimization strategy. After that, I will show the experimental evaluation of our proposed method. Nowadays, data collection from individual users to collector is more and more pervasive. However, this may come with privacy issues. As an answer to privacy-preserving data collection, local differential privacy, always say LDP, is a privacy model where each user locally perturbs their data and then send it to an untrusted data collector. Currently, randomized response has been the predominant technique for LDP. Specifically, when a user is asked, are you HIV positive, then the answer may be yes or no. And for the sake of privacy, this user may give the true answer with probability p and an opposite answer with the probability 1 minus p. LDP is a promising privacy-preserving model. It has been deployed in many real products by several major internet companies for simple data types, such as the categorical data or the numerical data. And currently, there is no existing LDP solutions for key-value data, which is an extremely popular data model. Here is an example to collect app usage data in smartphones, where the key is the app identifier and the value is the screen on child of each app. To collect this key value data with LDP, we need to design a new approach. There is a naive solution for key value data perturbation. For example, for this key value pair, cancer is a disease, and the key cancer is a disease, and the value 0.2 is its diagnostic value. Suppose we use the existing method for categorical data, KRR, to perturb cancer to fever, and use the existing method for numerical data, harmony, to perturb 0.2 to 0.4. Then the perturbed key value pair is like this, fever 0.4. However, as we see in the left table, each disease has its own value domain, and this 0.4 is not in the domain of fever. Therefore, we say key value correlation is a big challenge for key value data perturbation, since this is due to the key value correlation. For key value data, we focus on two fundamental estimations, that is frequency estimation over keys and mean estimation over values. As both frequency and mean are associated with a key, our first step is to convert a user's key value pair set to its canonical form. Here is an example of data conversion. Suppose there are 6 keys in the universe. A user has 4 key value pairs with key ID 1, 3, 5, and 6. Then as for its canonical form, these 4 pairs will be set into the positions of index 1, 3, 5, and 6. And other positions will be marked with an empty key, whose key and value will be set as 0. After key value pair conversion, we consider to design a protocol for key and value perturbation. Here, we also give an example that consists of several users and only one key in the universe in the left table. We need two phases for key and value perturbation, respectively. For key perturbation, we can use randomized response directly, and then the value perturbation is according to the perturbation results of the key. Here the problem is when 0 is perturbed to 1, we need to assign a new value to it, shown as this V star. As users has no background knowledge about the true values, how to choose this value is a new problem. Here we use harmony as a building block, and we further correct outliers by harmony. As will be seen in the experiment, this correction will significantly improve the accuracy. Here we give our baseline approach, where the assigned value is randomly drawn from the value domain. The framework of data collection is shown in this figure. As we see, this is a one-type data collection, so it has low communication bandwidth. However, this approach cannot achieve satisfying accuracy due to its poor assignment of the V star, since V star is just randomly drawn from the value domain. To improve the accuracy, we propose an iterative model, PrivKV, which assigns a V star as the mean of all values. This figure shows the framework. Here, we add step 6 and step 7 as a feedback to improve the accuracy. In this model, the output mean of the previous iteration becomes the assigned value of this iteration, so that the mean estimation will gradually approach the ground truth. With multiple iterations, this approach improves the accuracy of mean estimation. However, it also comes with a high communication bandwidth, as multiple interactions between users and the data collector are needed. In addition, it also needs a number of iterations to be determined in advance. Intuitively, we may think of a question: how many iterations are enough? In reality, it is quite difficult to determine this number. To this end, we propose PrivKV plus. Here we define a cost function f in terms of r, the number of iterations. You can see F1 is the accuracy cost, and the F2 is the communication bandwidth. By minimizing this total cost F, we can derive an optimal number of iterations, R here. Obviously, this approach strikes a balance between accuracy cost and the communication bandwidth, and has the lowest total cost. But it still needs to consolidate cost. Here is a comparison of these three proposed solutions. PrivKV is based on PrivKV, which improves the accuracy. And further, PrivKV plus strikes a balance between accuracy and communication bandwidth. Based on the above three approaches, we further propose an optimization strategy by applying batch processing and virtual iterations. That is to say, in each batch, only the first iteration is really executed, and the others are just virtual iterations, where the collector can directly predict the estimate mean without user involvement. And further, the mean prediction can be derived by a recursion. Show as this. This optimization strategy has two advantages. First, it reduces the network transmission overhead between user and the data collector, as users are not involved in virtual iterations. Second, since virtual iterations do not cost any privacy budget, real iterations can be allocated more of it, and therefore improves the estimation accuracy. Here we show some experimental evaluation. As for the dataset, we conduct experiments over 6 datasets. The first 3 are synthetic datasets whose keys and values follow a Gaussian power law and a linear distribution. And the other 3 are real datasets. As we see, the first 2 are app usage data, whose key is the app identifier and the value is the screen on time of a user in a certain period. The third one is about sales records. To measure the accuracy of the estimated frequency and mean, we use 2 matrices, say relative error and mean square error. As for the frequency estimation, we show the results of PrivKVM comparing with 3 existing methods. We observe that our method is more accurate than the other 3 existing methods. And for all methods, we observe that more frequent a key, more accurate the result. And overall, PrivKVM is less affected by the frequency of a key. Further, for mean estimation, we show the results of PrivKVM comparing with the other 2 combinations. Here, a value perturbation primitive in PrivKVM is replaced with 2 existing methods for mean estimation. We observe that PrivKVM is more accurate than the other 2, especially for a small privacy budget. To show how well the key value correlation is retained, we show these 2 figures. Here, the black line denotes the true Gaussian distribution. We observe that the estimate mean of PrivKVM follows a very similar distribution as the real mean in the left figure. However, a combination method, KRR and harmony, the result seems very flat. It also deviates from the true distribution. This indicates key value correlation is well retained in PrivKVM. Here is our conclusion. We propose 3 solutions for key value data collection with local differential privacy, and we further compare these 3 approaches in terms of estimation accuracy and the communication bandwidth. We theoretically prove the estimation is unbiased and always converge to the ground truth. And we also optimize our solutions to further improve the performance under a large privacy budget. That's all. Thank you.
Any questions? So there's one microphone in the middle, and then I have one in the front here.
So do you assume each user has a multiple key value pairs or just one key value pair?
A set of key value pairs.
So in this case, the privacy guarantee, is that per value, per pair privacy or per user privacy?
For user privacy, we use the sampling a set of key value pairs, and then we don't just allocate the privacy budget for each key value pair evenly. We just use the sampling technique.
Thank you.
Hi, I'm Damien from Google. Another way to do sort of quasi-local differential privacy data collection is the ESA infrastructures like the encode shuffler analyzer. I don't know if you've heard of this. Have you compared this to these methods where, you know, instead of having only one direct communication between client and server, you have a shuffler in the middle that encrypts stuff and stuff?
Sorry.
There's been papers for doing private data collection that are based on the two-step infrastructure, like encode, shuffle, and analyze. And I was wondering how your method compares to that.
Do you mean except for the frequency estimation and the mean estimation, can we adapt this method to other query? I think our solution is task specific, so for now we only focus on the frequency estimation and the mean estimation. Yeah.
Maybe a related question. Have you tried non-local differential privacy and see whether how much utility loss there is as compared to local?
Actually, we don't compare this in the as for the quantity, since they are focused on different settings. The centralized differential privacy focus on two neighboring dataset, while the local differential privacy consider two tuples, just neighboring tuples in the local setting.
So you're saying they're incomparable?
I think they are different settings, so we don't.
Okay, any other questions? All right, let's thank Vicky one more time.